Let's talk about a few other antiderivative rules. So let's do exponential. The integral of an exponential function with base e. Remember that the derivative of e to the x was just e to the x. And so just like that, the antiderivative of e to the x is just e to the x plus a constant. Notice that only works if my variable there is just an x. If there's something like an x squared, we'll have to handle it differently, which we'll talk about later. So this is just for e to the x. We also have rules for bases other than e. Remember that if we took the derivative of a to the x, that derivative was a to the x, and we would multiply by natural log of a. So it's similar here, we're just going to divide by natural log of a instead. Remember, we're going the opposite direction. So with derivatives, we multiplied by natural log of the base. Here we divide. So in number 5, I'm integrating 5e to the x dx. That is just 5e to the x plus c. Just stays exactly the same, but don't forget to add your constant. If my base is anything other than e, so such as 6 to the x, my antiderivative is still going to be 6 to the x, but I have to balance by multiplying by 1 over natural log of 6, and then plus my constant. You could do that with e, but natural log of e is just 1, which is why we don't have to worry about it. Now, since we were talking about exponential functions, you might be thinking about logarithmic functions. You actually will not learn in AB calculus how to integrate natural log of x. It's actually something in the BC topics. But you do want to think about, if you remember, what was the derivative of natural log of x? It was 1 over x. And so what that means is the antiderivative of 1 over x is natural log of x. However, I do want you to pay close attention. It's actually natural log of absolute value of x. This has to do with a domain restriction. So natural log of x, when I look at the original function natural log of x, I can only plug in positive values of x. So this domain has already been restricted when I take the derivative. But here, when I'm integrating 1 over x, I can plug in anything besides 0. And so I could plug in negative numbers to 1 over x. And so in order for me to have the same domain, so I can plug in negative numbers like I could to 1 over x, I just have to put an absolute value sign there. So whenever we're taking antiderivatives of 1 over x, which is also, this was the other special case, we were talking about x to the negative first dx. That is natural log absolute value of x. So number 6, we're going to integrate 5 over x dx. So you want to think of that as 5 times the integral of 1 over x dx. Remember, the constant just comes along. 5 times natural log absolute value of x plus c. Now, we talked about antiderivative sum in 6.4, and we also talked about this theorem of calculus called the fundamental theorem of calculus. So whenever you hear fundamental, you should realize that's something that's very important. And what that tells us is that when we have a definite integral, this is the integral from a to b, I can evaluate that by finding the antiderivative at b minus the antiderivative at a. So antiderivative at the top minus the antiderivative at the bottom. Now we focused on area with that, but let's do this algebraically now. So in number 7a, we have the integral from negative 10 to 4, or sorry, negative 2 to 4 of 10 dx. 10 is our integrand, our function. So our first step is to find our antiderivative. And the antiderivative of 10 is 10x. But after I find that antiderivative, I still need to evaluate from b to a. And so what I'm going to do, I'm going to put brackets around this. Sometimes you'll just see it with a bar at the end, but I prefer to use brackets so I can see everything that I'm plugging in. And I'm going to write my bounds now at the end. So this says I've already taken the antiderivative, and now I'm going to plug in these numbers. So then I do top minus bottom. So 10 times 4 minus 10 times negative 2. So that gives me 40 plus 20, which is 60. Now we have already actually talked about how to integrate this function when we had a rule about when we integrate a constant function, and we said it was that constant times the number at the top minus the number at the bottom, because this would have the area of a rectangle. Notice that's the same thing I did here. This is just distributed compared to what I had up here. I would have gotten 60 the same way. So you can actually do that same rule whenever you see a constant here, or you can take the antiderivative and plug things in. But just realize you do get the same exact answer either way you do that. Now let's get on to a more complicated function. In part B, we have the integral from 0 to 1 of x squared plus square root of x dx. Now again, I prefer parentheses there. You don't necessarily have to have them. The dx tells me where the end of the integral is, so I can tell everything that I'm integrating. Take your antiderivative first. Antiderivative of x squared is x cubed, and then divided by 3. So add 1 to your exponent and divide. And then for square root of x, remember that's x to the 1/2. So leave a space, x, my new exponent is 3/2. My coefficient is the reciprocal of that, 2/3. Now I don't need my plus c here, because what will happen, I should have written it over here. If I had 10x plus c, I would have had 10 times 4 plus c minus 10 times -2 minus c. My c's will cancel out. So when I have definite integrals, I do not need to write the plus c. It won't hurt you if you do, but they will just always cancel out. Now I do need to evaluate from 0 to 1. So I'm going to plug in 1 first, top number first, 1 over 3 plus 2 over 3 minus, and now we have multiple terms here. You want to pay attention to parentheses, minus 0 plus 0. Well, this is just 0, so it works out for us here. This is just 1. But this is one of the most common mistakes that we see is people forget to use parentheses here or distribute that negative through. So just be really, really careful with your notation. All right, in C, we're integrating from -pi/4 to pi/4 2 secant squared theta d theta. So our antiderivative of 2 secant squared is 2. Remember, the derivative of what function is secant squared? That is tangent of theta. And then I evaluate from -pi/4 to pi/4. So that means I have 2 tangent of pi/4 minus 2 tangent of -pi/4. Now, if this were a problem on the free response on an AP test, you could actually leave your answer right here. I don't have to evaluate that trig function. But let's say this is multiple choice, you're going to have to know how to do that. So tangent of pi/4 is 1, so this is 2 times 1, minus 2 times tangent of -pi/4, that's the fourth quadrant, tangent is negative there, that is -1. So I have 2 plus 2, which is 4. In part D, we have the integral from 4 to 9 of 1 minus square root of t over square root of t. Remember, those are t to the 1/2. Here, when we're dividing by square root of t, it's like distributing t to the -1/2 to my terms in the top. So what I'm integrating, I would suggest you rewrite this first whenever you have radicals, especially a complex radical like this. I'm integrating t to the -1/2 minus 1 dt. So essentially 1 over square root of t is t to the -1/2 minus square root of t over square root of t is -1. Now I'm ready to take my antiderivative. So the antiderivative of t to the -1/2, leave a space. T, my new exponent is positive 1/2. My coefficient then is the reciprocal, 2. Minus the antiderivative of 1 is just t, evaluated from 4 to 9. Now at this point, it might help you to rewrite, instead of a 1/2 exponent, think of it as a radical. So we have 2 square root of 9 minus 9, that's our first term, minus 2 square root of 4 minus 4. Again, pay attention to your parentheses here when we have that negative. So this is 6 minus 9, that's -3, minus 4 minus 4, that's 0. So my answer is -3. For part E, we're integrating e to the x from 0 to natural log of 5. My antiderivative of e to the x is just e to the x, very easy. And I'm evaluating from 0 to natural log of 5. So I'm going to have e to the natural log of 5 minus e to the 0. Again, this is an acceptable way to leave your answer, but it won't be shown like that on a multiple choice. E to the natural log of 5, the e and the natural log cancel out, so we have 5. Minus e to the 0, that's just 1. So my answer is 4. For part F, we're integrating from 1 to e squared of 3 over x dx. My antiderivative of 3 over x, this is that important one that we talked about above. That is 3 natural log absolute value of x. And I'm evaluating that from 1 to e squared. So I have 3 natural log. Now, absolute value of e squared is just e squared because e squared is already a positive number, minus 3 natural log of 1. So the absolute values are really most important if you're evaluating on a negative interval, which isn't the case here, but you do have to be careful of that. Again, this would be an okay way to leave your answer on a free response, but we're going to simplify it. 3 times natural log of e squared cancels, so 3 times 2 minus 3 times natural log of 1. Natural log of 1 is just 0, so I get 6.